Today we're in for a real treat. Welcome. Today we have kind of an annual thing that we like to do, which I won't describe too much because we have the right person to do that. You've seen in the last few sessions some illustrious alumni, and now you're going to see people who will soon be illustrious alumni who are doing cutting-edge research in the labs around campus. So with that said, it's my great pleasure to introduce an old friend, a young friend, a friend I've had for a long time, Dr. Jennifer Milne, who's actually in her own right an outstanding biochemist and plant biology expert. But one of her jobs on campus here is to lead the advanced research projects at the Precourt Institute for Energy, which has many parts of the job. She also works for the New Door School Accelerator on more, applied outreach things. So she may just be keeping in touch with some of these speakers the next few years. And so Jenny will tell you just one of the many important jobs she does for the Precourt Institute and the Precourt director, and it will become immediately obvious what that job is. So without further ado, please join me in welcoming Dr. Jennifer Milne.
Thank you very much, John, for that very kind and generous introduction. So it is my absolute pleasure today to welcome you here to hear presentations from our students. So these students were part of our Summer Energy Student Lecture Series. And what that is a showcase, an opportunity to showcase the work that the students do every summer. This year we had 16 Stanford students present their work, and the purpose is to give them an opportunity to share their work with an audience that may be broad and technical to some degree, but not in their exact areas of research. So it's a good practice for them to communicate their cool and exciting research and the results that they have. So we have 4 that we selected last year. Before I introduce them, before I introduce our 4 distinguished lecturers, I'd like to thank all the folks who organized the program. So let's start with Angela Kai. She was the student seminar manager and she facilitated the seminars. And then Ms. Bernardo helped with recording the lectures and providing one-to-one feedback with the students. Rachel Madison, I think, who's here today, managed the series. And then our judges, more than 4 this year, Richard Sassoon, Audrey Yao, my fellow colleagues at the Precourt Institute for Energy, and then some of our accelerator friends. So Jeff Brown, Shamali Pandit, and Jama Aguilera also joined us on the judging panel. So without further ado, I'll read out all 4 bios for the students, and then they'll give their talks in order, and then we'll ask to hold the questions until the end. So we'll ask also that you remember any questions you might have for the first speakers. However you want to do that, write them down, or maybe you have a great memory. So the first speaker I'd like to introduce is Jenny Liccardo, and he is a PhD candidate in chemical engineering here. He's mentored by Professor Stacy Bent and Matteo Carnello, and his research focuses on the synthesis of tailored materials for heterogeneous catalysis. I'll keep these all short. You can read on the website and the email that went out further about each of these interesting folks. So the next one is Kristen Abels. She's a 4th-year PhD candidate supervised by Tarpeh in chemical engineering as well. And her research centers around the assessment of polymeric membranes for ion-selective separations, and mostly for lithium recovery from battery waste and brines. Then the 3rd speaker is Mohammed or Jabs Al-Jubran. Hopefully I got that right. Great. He's also a 4th-year PhD candidate in the Department of Energy, Science and Engineering. He's supervised by Professor Roland Horn, who I believe is in the audience today. Thanks for coming, Roland. And his research focuses on modeling and optimizing the techno-economics of geothermal power and energy storage. Jabs actually is a co-founder already of a company, so I'm going to put that in there, and maybe Jabs can tell you all about that in the Q&A. And then lastly but not least is Shraddha Sapru, and she's a fourth-year chemistry PhD student, co-advised by Aruma Jumdar and Matteo Carnello. And she works in the field of heterogeneous catalysis for energy and sustainability applications. And you'll hear more now. I'm not going to make you wait any longer. So first up, we have Jenny. Would you like to come up? Yeah, pass it over to you. Thanks.
Thank you so much for the introduction. Hi everyone, I'm Jenny, and today I'd like to teach you a little bit about stability of encapsulated platinum catalysts. Why should you listen to this first? Well, people out there are stealing catalytic converters. They're doing it here at Stanford. They're doing it especially in Wilbur Hall. So don't go there parking your hybrid vehicles. I'll tell you a little bit about why they're stealing your catalytic converters and how I made some materials that represent relevant materials for this system and how we studied those to stop this from happening again. First of all, what are catalytic converters? They're systems that take care of noxious emissions coming from your internal combustion engine and convert gases like nitrogen oxides, carbon monoxide, uncombusted hydrocarbons, and turn them into non-harmful chemicals like nitrogen, carbon dioxide, and water. We do this with very precious elements like platinum, palladium, rhodium, supported on less precious metal oxides like alumina. To give you an idea of how precious these elements are, here is platinum versus gold production. We think of gold as an extremely rare element, but platinum is not even a tenth of what we produce in gold. And it's also not well distributed globally, and we know how international trade can be a tricky topic these days, so it would be great if we could make the best use possible of these elements. But they have not been, we've not been able to replace them, mostly because of what we call cold start requirements. So what this means is that you need to be able to perform these transformations the moment you turn on your car and your engine is at low temperatures, and these very rare elements are extremely active, so that's why we use them. However, they will also have to endure extremely testing conditions, very high temperatures, oxidizing environments, steam present, and what this means to your system is basically that it will not be very stable. So what I show here is a relevant catalyst. This is platinum supported on alumina, and those barely visible bright specks are platinum clusters. You want them to be as small as possible so that you maximize active surface area. But when you put them in relevant conditions, then it's much easier to see them because they're growing into huge crystals. And basically what's happening is what people refer to as sintering or particle growth. You're getting these very small clusters to grow, and what happens is you lose surface area in this process and ultimately decrease the efficiency of utilization of such precious element like platinum. So how do you stop this from happening? In a conventional catalyst where your platinum is supported atop your alumina support, you will observe at high temperatures in oxidizing environments the growth of these nanoparticles in much larger clusters. But if you're able to encapsulate it in a network, then we've observed that actually in the same conditions, the catalyst remains very stable. So this was not super clear how it happened because this encapsulation technique does not allow for fine control of your encapsulating environment. And my job there was to try and understand how this is actually stabilizing your platinum nanoparticles. So how they are unstable, first let me show you how sintering happens, how particle growth happens. In these conditions, 800 Celsius in the presence of oxygen and steam, smaller platinum nanoparticles will volatilize and build this larger platinum nanoparticle, ultimately losing surface area. So this is what we're fighting against, and we're looking into encapsulated systems, but this time I decided to make these catalysts in a much more controlled way. I encapsulate them again in aluminum oxide as we had done previously, but now I do it through atomic layer deposition, which is a technique that allows you to deposit one atomic layer at a time, which makes it extremely interesting and useful for controlling the thickness of our encapsulating layer, our protective layer. It's through a sequence of self-limiting reactions that you're able to build these films of a desired nature, and then you can cycle through these self-limiting reactions to build thicker and thicker films, which is what we do. We start with a platinum supported on alumina, and then we encapsulate it with a thin overlayer of aluminum oxide in what we call a short exposure procedure, and a thicker aluminum oxide overlayer. When we look at these materials, we have here the starting catalyst, which is just platinum supported on alumina, and we observe bottom left particle size distribution and top right the average particle size, we start with 5 nanometer platinum, and this is not changed after we encapsulate it. So we can keep the nanoparticle size constant throughout this atomic layer deposition procedure, and then we can test these catalysts for their reactions. So we have here CO2 production against 1 over temperature. You want to be in the top right of this graph when you're testing your catalyst. Here we're observing the performance of a supported catalyst to begin with. However, after aging, this catalyst drops in performance significantly, deactivating. When you coat it with a tiny bit of aluminum oxide, the performance is comparable, and remarkably, after relevant conditions of aging, this catalyst is at all not deactivated. And then when you encapsulate it with a lot of alumina, you begin with a catalyst that is much less active. However, after spending some time in relevant conditions, you achieve much greater activity. And in summary, if you have these encapsulated samples, you can have a catalyst that is up to 2 times more active than a normal supported sample. When we look at these catalysts, we confirm that a normal platinum-supported catalyst will grow into much larger particles. We had particle size distribution around 5 nanometers. Now it's much larger than 20. Top is just the age sample, and at the bottom we're comparing it before and after. This is not true for the encapsulated systems, where we retain a much smaller platinum particle size. We're effectively stabilizing them at high temperatures from growing into these much larger clusters. So how is this happening? Well, we were thinking before we need to fight against that volatilization mechanism. So are we actually stopping platinum from volatilizing? And we try to answer this question by measuring the volatility of our particles in an experimental setup where basically you'll have a geometry where platinum is allowed to vaporize and be taken away from your reactor. And then you can monitor the platinum content over time. And if volatility is your driving force, after some time, you'll basically be left with no platinum. And so this is what this experiment shows. Bottom to the top, you'll have in yellow the supported platinum on alumina catalyst. The platinum content over time decreases as more and more of that platinum is volatilized, and it actually goes to 0 after a little bit more than an hour. Whereas this is not true for the encapsulated systems, where now this overlayer is actually able to retain the platinum up to more than 50% of the original content. So in conclusion, how we stabilize platinum in encapsulated systems. In a non-encapsulated system, platinum is free to volatilize and grow into much larger crystals. But once you build an encapsulating network, you're now able to hinder this process, slow down the volatilization of platinum oxide, and so you retain much smaller particle sizes. With that, I'll end, and I'll thank all the people that made this work possible, the funding sources, and your fair attention. Thank you so much.
Wonderful. Thank you very much, Jenny. That was great. And next up we have Kristen. And just as a reminder, she's going to talk on membrane-based lithium recovery, composition and driving force effects in ion-selective separations.
It's a real pleasure to be here and share some of my work on membrane-based lithium recovery, and specifically looking at ion-selective membrane development. First, I'll motivate why we care about lithium recovery, and I see a lot of laptops in the audience. Perhaps you all have smartphones. These all have lithium-ion batteries in them, and lithium batteries are more important for just our personal devices. They're also powering the clean energy transition. So much so that the U.S. Department of Energy has identified lithium as one of the electric 18 critical materials, both due to its high importance to the clean energy transition, but also its high supply chain risk. So this creates both environmental and economic incentive to really bolster our domestic lithium supply via recovery from alternative sources. Some examples being oil and gas produced water brines or geothermal brines, and also lithium-ion battery waste. But the challenge with both of these sources is they're pretty complex mixtures. For instance, brines contain a lot of sodium and calcium and magnesium in addition to lithium, but at much higher concentrations. And then the cathode active material from battery waste also contains transition metals like nickel and cobalt. So the challenge becomes, how do we separate lithium from these really complex mixtures to produce a high purity product? And right now, industry typically relies on extraction and adsorption to do this separation, which are technologies that lie right in the middle of the energy intensity scale for different separations. So in our lab, we're asking ourselves whether we can develop ion-selective membranes to do this separation, but in a less energy-intensive way. The problem with membranes is that right now, current commercial available membranes typically operate based on either size selectivity or charge selectivity to separate solutes from a mixture. And when we look at the application of lithium recovery, where we're trying to separate out one positively charged ion from a mixture of many different positively charged ions that are all very similar in size, these two selectivity mechanisms don't quite cut it. And that's why current researchers in the membrane separation field are looking to the development of new ion-selective membranes where we incorporate these functional groups called ligands that could enhance the transport of one ion over others. And this is really considered one of the next frontiers of membrane separation science, so there's a lot of work that needs to be done to develop high-performing materials. Some of these challenges include finding just the right Goldilocks ligand that will enhance an ion's partitioning into the membrane without hindering its diffusion through the membrane too much. And then on top of that, picking just the right Goldilocks ligand is hard because most ion-ligand interactions are reported for homogeneous organic solutions where that environment for coordination differs drastically from what an ion-ligand pair might experience in a membrane, especially if we consider the application of an additional driving force like electric potential to enhance ion transport. So based on some of these challenges, there are a lot of fundamental questions that we need to answer in order to develop these ion-selective membrane materials. And some of the questions that we were asking ourselves in some of our previous work are specifically, how does ligand content within a membrane impact ion transport? And also, how does the electric potential driving force you apply for a separation impact your separation selectivity as well? So to answer these questions, we synthesized a whole library of membranes of different chemistries, and we tested them for the transport of different ions like lithium, sodium, magnesium, and nickel. And our two main metrics that we tested were for permeability, which is essentially the rate of ion transport through a membrane, and then also perm selectivity, or the ratio of two ions' permeabilities. So for this presentation, I'll focus on a subset of membranes that just contained pyridine as our ion coordinating ligand at 0 to 50 mole%. And we'll look at the transport of lithium and nickel, which are two ions that we might want to separate out of a battery waste stream. The reason that we'll look at these two ligands is because lithium has very weak interaction with pyridine, whereas nickel has much stronger interactions. In fact, in solution, nickel can form a 1-to-1 complex with pyridine, all the way up to a much stronger multidentate complex with pyridine ligands. So based on their two different interaction strengths with pyridine, we see very different trends in ion permeability as we go across our membranes containing increasing pyridine content. We see that lithium permeability is relatively unaffected as we increase our pyridine content due to that weak ion-ligand coordination. But when we look at nickel, we see a gradual decline in permeability as we increase our pyridine content. And we attribute this to the fact that it's much more likely for nickel to form these strong multidentate interactions at our higher pyridine contents, where it's more likely to have adjacent pyridine ligands on the membrane backbone. And because we see these two very different trends in permeability across our membranes, when we shift to separation experiments, where we're trying to separate out lithium and nickel from some feed solution into a permeate solution, we also see an increase in lithium-nickel perm selectivity as we increase our ligand content. So this is really interesting because up until this point, while people have studied the impact of incorporating ligands like pyridine into our membrane, no one's really looked at the effect of changing that ligand's content in the membrane, and here we can see that it has a somewhat substantial impact on the separation performance. What's interesting beyond this as well is that our higher pyridine content membranes increasingly favor nickel absorbing into the membrane. So our partitioning selectivity for lithium over nickel goes down, which is exactly opposite what we see for the overall selectivity in ion transport. So given that permeability is a product of partitioning or absorption into the membrane and then mobility through the membrane, this is suggesting that our lithium-nickel mobility selectivity must be getting increasingly large in order to give us this overall upward trend in perm selectivity. So this is another insightful observation because this is telling us that our mobility effects in these membranes really appear to be outcompeting the partitioning effects in our overall perm selectivity trends. Specifically, our strong pyridine coordination with nickel is hindering nickel's mobility more than it's enhancing its partitioning, leading to the trends that we observe here. We also went one step further and we tested out our highest pyridine content membrane in an electrodialysis setup, which is something that you use in industry where you apply an electric potential driving force to really push ions across the membrane and increase the process productivity. One concern we had for lithium-nickel separation is that the +2 charged nickel ion might feel the electric field more than a +1 charged lithium ion, and that could potentially diminish our perm selectivity. But fortunately, when we tested our membrane out under electrodialysis setup with increasing applied potential strength, we actually observe a near doubling in lithium permeate concentration, or permeability essentially, whereas nickel permeability was relatively unaffected even as we increased our applied potential. So this is suggesting that nickel pyridine coordination is sufficiently strong to keep nickel from permeating across the membrane even at the highest applied potentials that we studied. And because of this, we also see an increase in lithium-nickel perm selectivity as we increase our applied potential as well. So this is really encouraging because we're seeing both enhanced productivity and enhanced selectivity as we increase our applied potential driving force, which is promising because there's typically a trade-off between these two performance metrics in membrane-based separations. So this is a really quick overview of some of the work that we've been doing to better inform structure-performance relationships in these types of ligand-functionalized membranes, where we specifically looked at ligand identity, ligand content, and driving force effects on ion transport. Moving forward, we're testing out other effects of tuning membrane properties like water content on ion transport, and the big goal for all of this work is to really help inform fundamental design rules in this next frontier of membrane development. So with that, I'd just like to finish up by thanking my lab group, the Tarpeh lab, my advisor, Professor William Tarpeh, 2 postdocs, Hamilton and Shi, who helped a lot with this work, and our funding sources, and the lovely audience for your attention. So thank you.
Wonderful. Another great job. Thank you, Kristen. Both have really great results there. So it's super exciting. So next up, I'd like to welcome Mohammed, or Jabs, as he likes to be known. And he will be talking about techno-economics of enhanced geothermal systems across the continental United States.
Hi, everyone. My name is Jabs Al-Jubran. I'm a fourth-year PhD student working with Professor Roland Horn at the Stanford Geothermal Program. And we'll spend the next few minutes talking about geothermal energy. Since the early 1900s, we've been using hydrothermal resources to generate power. And a hydrothermal resource is made up of 3 main elements. You target a hot rock down underground that has naturally occurring fractures filled up with water. So you tap into that, you extract hot water or steam, run a turbine, and make up power. The challenge with those is that they are very limited to a specific range of geologies and hence do not scale up as well. So people have come up with this idea where they target just hot pieces of rock using enhanced geothermal systems, or EGS, where you drill a couple of wells, create fractures in between them, circulate cold water that sweeps heat, gets produced to generate power as well. The Department of Energy estimated that the US has a potential of EGS that is 5,500 gigawatts. That's just over 4 times the installed power capacity in the United States as it stands today. So it's significant. Now, our goal today is to revise these models they use to come up with these estimates and evaluate the techno-economics of EGS nationwide. The question that we ask is, what is the levelized cost of electricity, or LCOE, and return on investment, ROI, of EGS? And we do this in 3 steps. We build a thermal earth model of the subsurface. It tells us what temperature is. We feed that into a techno-economics model, and it tells us what the economic potential looks like. Starting with the first piece, I first reviewed the literature, and I figured, you know what, I'll just use something from there. And then I found this Southern Methodist University SMU work from 2006. They built a temperature model down to 10 kilometers, starting at 3 kilometers. And then there came other people at NREL that extrapolated this to surface. I was like, bingo, I got it. 1/3 of my PhD is done. But that's not the case. So when you stack them together, at the crossover of 3 kilometers, temperature decreases on average by 40 Celsius, and that's non-physical. So they were made to function separately, but not to be stacked. So I was not allowed to do that. Rather, I decided to build a model, for that matter, that spans depths and be physically consistent. I followed a physics-informed graph neural network approach. So think of the US as a 3D volume. You mesh it Think of grid cells as nodes. At each node, you might have some physical quantities like gravity anomaly, magnetic anomaly, etc., etc. Some other nodes might have thermal quantity measurements, which we call Y, temperature, rock thermal conductivity. We want to predict those. That's what makes up a thermal Earth model. We connect the nodes with edges, and hence we create a graph. We apply your favorite graph neural network. We call this one edge convolution, and it does some magic, a jungle of math and linear algebra, and it spits out good results. But the results are not constrained, so we have to put in physics on top of it. And if you recall, you get a slice of Earth. You have the core, mantle, crust, heat flows from the bottom to the top. You top that up with your radiogenic heat production from isotopes like uranium, potassium, and thorium. You express your steady state Fourier's law of conductive heat transfer. Simplify that. You get this expression on the bottom: temperature, thermal conductivity, heat flow, radiogenic heat production. And the model now needs to approximately satisfy this expression besides fitting the data. And voila, it gets you predictions that look like what you have on the right-hand side. The color bar is temperature, hot is high, blue is cold. 6 kilometers, 6 layers from top to bottom. Temperature increases, we look good. It's diffused spatially, we look even better. We try it against actual data from geothermal wells. Black dots are measured data. Our model's in red with an uncertainty band. We look good. So we like this model. What we do next is we feed it into the techno-economics model, which I'm not going to describe how we developed today, but I want to jump to the results directly. But one thing I want to highlight: in geothermal, we have to drill, and that's a big cost component. When it comes to drilling, the most recent and only commercial EGS project was actually developed by a company called Fervo Energy in the United States, and the co-founders of that were students of Professor Roland Horn as well, so they came out of Stanford. And they started with a project in Nevada, they called it RED, and they are currently working on a 500 megawatt project in Utah called CAPE. What they noticed was that from left to right, the more wells they were drilling, the better they were getting at it. And the drilling cost went from $1,000 per foot to $500 per foot. So it's about 50% improvement. So we do our economics with respect to these two rates. We call them the 2022-2024 drilling rates. So let's look at the baseline 2022 drilling rates. We compute the economics across the country. Color scale is LCOE in dollars per megawatt hour. Blue is not favorable, high. Red is favorable, low. We like that. What we see is that considering these drilling rates, EGS is economically competitive in the Western United States compared to the average revenue of $70 per megawatt hour. So there's a lot of potential for EGS. And if we consider the advanced drilling rates, advanced already accomplished by Fervo, as a matter of fact, now the country lightens up. Now EGS is competitive economically over more than half of the United States. So that's great news. How about it's being investable or not? We have to look at the return on investment. Now blue is high, which is good. We like revenue. Red is bad, not good. We see that on the western side of the country, EGS is investable with an annual average ROI up to 16%, which is competitive for investors in the energy sector. This really takes us back to this one slide that I want you, if anything, I want you to remember this one slide. That's exactly all that we did, and it's the summary of it. We built a thermal Earth model, a techno-econ model. We figured out the economic potential of EGS across the country. All of the work is published. You also have GitHub repos and ArcGIS maps that you can look at and play with. And the thermal Earth model is also hosted on a Stanford server that is stem.stanford.edu. You can go out there, can play with it, find where you live, maybe click on it. You get a temperature profile down there. If it's hot enough, maybe you call up a geothermal company and develop, and then give me a 10% royalty. How about that? And the rest of the data and the code base is also available on the web. And with this, I'd like to thank you and conclude.
Wonderful. Jabs, thank you so much. Another great talk. And how are those questions coming along, everybody? Getting ready? So our final speaker today is Shraddha, and she will speak on dual function materials for integrated carbon capture and utilization.
Hello, everyone. Thanks for being here today. And I think we're all doing great on time, so I'll also try to keep it simple and quick. I'm Shraddha, and today I'm going to talk to you about dual function materials for CO2 capture and conversion. So first, what's CCUS? That stands for carbon capture, utilization, and storage. So basically, it's this multi-step process which first involves the capture of CO2, which can be from industrial sources or directly from the air. Then you transport this CO2 either to the site of storage, where it can be permanently stored underground, or you can use it for making fuels and chemicals. We require this because a lot of hard-to-abate sectors like cement and steel will still require capturing of CO2 so that we can convert it to useful chemicals. And for this process, I'm specifically looking at CO2 capture and conversion. So that involves all of these steps, as you can see here, which is the conventional process as of today. It starts with the CO2 capture step, and then you have the desorption step. Desorption is basically separating the CO2 from the absorber, and this is the most energy and cost-intensive step as of today. Following that, it has the compression and the transportation steps, and then finally CO2 reduction, where this CO2 is then reacted with hydrogen to eventually give you the fuels and chemicals you require. This, as you can see, has several steps, and so people have recently looked into a novel process called reactive carbon capture, which eliminates all of these intermediate steps to directly take in your captured carbon and then react that with hydrogen to give you the desired chemicals. Now, what we are looking at is taking this CO2, reacting it with hydrogen through this reactive carbon capture process and making methane out of it. Now, you might be wondering, why are we taking one greenhouse gas only to make another greenhouse gas? And here's why. We take this methane, which can then be easily transported anywhere in all of the US using the already existing natural gas infrastructure, and then at that desired site, we can have a methane pyrolysis plant where you can then essentially decompose this methane to solid carbon and hydrogen. Now, this achieves two things. One, methane can now be used as an intermediate to go from CO2 to solid carbon, where you're essentially then using this solid carbon as either for sequestration or for advanced carbon material applications. Additionally, you can even have the transportation of hydrogen be done through this process, which is one of the major bottlenecks in the entire hydrogen industry today. Today, I will be focusing on the first part, which is the project I work on, but we actively have methane pyrolysis as a research area in our groups as well. Now, how do DFMs or dual function materials even achieve this? They have three components: an adsorbent A, a catalyst C, dispersed on a support. Now, what you do is in the first step, you flow CO2 through your reactor through this material, and then the CO2 gets adsorbed on these adsorbent sites. In the next step, you keep the reactor and material exactly the same, and you just switch to flowing hydrogen through it. This hydrogen reacts with CO2 at this catalyst site and then gives you methane. At the end of the reaction, once all of the CO2 and hydrogen have reacted with each other, you regenerate this surface again, and then you can switch back to flowing CO2 through it, and thus this can be done in a cyclic manner. As of today, ruthenium is the most well-studied catalyst for this reaction. Sodium oxide is the adsorbent, and both of them are dispersed on alumina. Now, what still remains to be understood really is like what the optimal loading of the catalyst and the adsorbent is, which can help us maximize the efficiency of this process. And additionally, how do these different components even interact with each other? For that, we intend to use colloidal nanoparticles for developing our catalyst, and this synthesis technique essentially helps us to individually vary every parameter to understand how it affects the overall reaction. Here I have an example from a paper published by our group, which essentially has palladium, which are these bright white spots that you see, dispersed on alumina. As you go from left to right, the amount of palladium decreases, but you are able to maintain the size distribution. So this synthesis technique essentially allows us to have independent control over these parameters, which a lot of conventional techniques don't provide otherwise. So using a similar technique, what I did was I prepared ruthenium colloidally, which is my catalyst of interest, and then prepared this library from 0 all the way to 1.5% to understand the effect of the catalyst alone. I prepared another similar library to study the effect of the adsorbent, but I'm not going to be talking about that today. So the way we do the synthesis is first we have sodium carbonate dispersed on alumina. We then calcine this to decompose sodium carbonate to sodium oxide. Now this sodium oxide on alumina is what serves as our adsorbent site. Then we add this colloidal nanoparticles, which is the 5 nanometer ruthenium particles, onto the adsorbent to finally get the dual function materials. Once we have the material made, we then perform these reactor tests, which first has this pre-treatment step to reduce the catalyst to its active metal form, followed by the CO2 adsorption step, where we flow dilute CO2 stream to be absorbed by the material, and then methanation, where you flow hydrogen to produce methane. Diving right into the results, when we look first into the CO2 adsorption step, this plot here has the amount of CO2 adsorbed as a function of the ruthenium weight percent. So two important things to note here is, one, when I have no ruthenium present in the sample at all, there is some amount of CO2 adsorption, but this nearly doubles when I add a small amount of ruthenium to the material. Additionally, after this, irrespective of how much ruthenium I add to the system, there is a very small increase in the CO2 adsorption. And so adding more ruthenium doesn't really affect the system much. This effect is a lot more pronounced if you look at the red circles on the right y-axis, where the lowest ruthenium amount has the highest CO2 adsorption. And this is actually really important because then we can use low amounts of ruthenium for this process, which makes this process more efficient, just because ruthenium is a lot more expensive. Now, to understand how ruthenium even enhances this CO2 adsorption, we looked back into the pre-treatment step as to how is even ruthenium increasing the amount of CO2 adsorbed. And we observed this formation of methane that you see here, which isn't really typical to be seen during that step. And what this led us to understand is that there is this chemical reaction which is occurring during that step. What essentially is happening is that there is some undecomposed sodium carbonate, which was a precursor, which is still left behind. That reacts with hydrogen in the presence of ruthenium as the catalyst to produce methane. And in this process, there are additional sodium oxide adsorbent sites which are created. And then these adsorbent sites can now take up more CO2, thus increasing the CO2 adsorption amounts. Thus, ruthenium actually plays kind of like an indirect role here to increase the CO2 uptake of our materials. We then looked into the methanation step, where here you can see as we increase the amount of ruthenium, the total time that it takes for the production of methane is going down. So more ruthenium really increases the rate of methane production, which is great. If we look at the total amount of methane produced, though, that remains pretty consistent across all the ruthenium percentages, which is similar to what we saw for the CO2 adsorption amounts. So this made us really wonder, how are such low amounts of ruthenium doing such a great job? And for this, we did a lot of in situ and operando characterization techniques, and this led us to a proposed mechanism, which I'm just showing you right here. So what is essentially happening is I have this sodium oxide on alumina dispersed right here. So first, CO2 gets absorbed in the form of these carbonate species. And so the carbonate which is present at the interface of ruthenium and the support is what gets converted first. So these carbonates right here first get converted to methane. And once those carbonates are lost, there is a slow carbonate migration across the alumina surface towards these ruthenium particles, which then results in further reduction. What this means is that even if I have just a little amount of ruthenium, as long as these carbonates are able to migrate to that ruthenium site, you can produce methane, which is why even small amounts of ruthenium are able to do this reaction really well. And with that, I hope I was able to show you how colloidal particles are able to disentangle catalyst and adsorbent effects, and additionally, the role of ruthenium, where it activates sodium carbonate and also enhances the rate of methane production. Currently, what we're also looking into is how we can really just replace ruthenium with nickel so that we use less of a precious metal and also move towards more realistic conditions. With that, I would like to thank everyone involved in this project, the funding agencies, and all of you for your attention. Thank you so much.
Marvelous. Thank you, Shraddha. Wonderful. Great talks. And an amazing job of keeping it to about 8 minutes per presentation. And that's really, really hard to do. So kudos to you all. And thank you, Noel, for smooth running a show. So questions. Anyone has questions for any of our 4 speakers? And maybe I'll ask, we have a couple I see already. If you don't mind, we'll ask all 4 to come up and stand here with me so I'm not on my own, so that it'll be a prompt for people to remember as well your presentation. So I saw one hand. Can you just put your, Len, you have it.
Can I run that? Yeah. 1 second. We got to get it in the mic to get it on the recording.
So I have a question about the round trip efficiency of the conversion of CO2 to methane. If you go to if you do the absorption and reaction and then drive it the other way to drive off the hydrogen at the other end, what fraction of the energy that was contained in the hydrogen to begin with do you end up with in the hydrogen at the other end?
Yeah, that's a great question. That is something we're kind of looking into while we're also trying to look into like the techno-economic aspect of this model. And in that, we're trying to understand what these kind of, something like that would result in. So I don't really have an answer to that question right now, but I would assume that you would at least be able to recover like 50% of it, but we're still in the work of like getting to a better number for that. Thank you.
Great, thanks. We have a good amount of time here for questions, about 8 minutes. So great. One here in the back. Can you say your name and then?
Hi, I'm Samuel Desai. My question is for Jabs about the geothermal presentation. In the introduction, they mentioned that you were working on geothermal optimization. And in your presentation, you talked about really creating this data set about geothermal potentials. So I'm wondering what your research is, what path your research is on now, and what you plan to do with this data.
All right, I think I'm back on. All right, well, thank you for your question. So there are some bits and parts that involved optimization that I have not spoken about today. And in particular, it's about how you dispatch geothermal. You can run your geothermal on pretty much 24/7 as much as possible with the same steady state flow rates from the wells, and you get your power output based on that. Or you could try to change your dispatch by including options like lithium-ion battery or hot water tank, where you store and try to dispatch during different times of the day. So that was some of the part or works that got modeled as part of that techno-economic model, which was called Flexible Geothermal Economics Model, FGEM, and that's where the word flexible comes from. So the optimization question was how to dispatch optimally with respect to power markets. And I'm happy to send you papers on that if you're interested.
Wonderful, thank you. More questions? We have 5-6 minutes left. Roland.
Hi, I'm Roland Horn. I have a question for you, Jenny, about your catalysts. You're coating the platinum with some other material that kind of stops it vaporizing, but presumably it's also stopping it doing its job of getting into contact with the material it's supposed to react with. So you looked at different cases, a thin layer and a thick layer. Is there an optimum? Too thin and too thick, somewhere in the middle, that would be optimal?
Yeah, thanks for the question. It's something we had explored in initial phases of the design of this project. We found later then when you actually put it to the test, like, I don't know if you remember, if I can pull up the slide, maybe it'll be clearer, but when you begin, you actually have a much less active catalyst if it's coated with, so the bottom left, the solid red triangles, that's the thick overlayer of aluminum oxide. That's like so not active, because as you're saying, I'm covering everything with this aluminum oxide film, but it turns out that when you put it to high temperatures, then the film itself restructures under reaction conditions and opens up a lot of pores for platinum to be again accessible. So we couldn't answer that question directly, because we found that in reaction conditions, the entire thing will change. It turns out that if you have a lot of it, you can still access platinum after this, and it really slows down. The more you have, the more it slows down the deactivation mechanism. So as long as you're within reason of an encapsulating layer, that's good. It was also cool to find that even with the tiniest amount, it's like around 1% change, you could also still stop it from happening, which was another finding that we thought was cool. Yeah.
Great. And I think that's testament to good presentations, because I don't think Roland is a catalysis expert, are you? So you managed to. Maybe you are. Great question. Next.
I have a follow-up question for Jenny. I'm Wiley. Thanks for the great talk. What does like very long-term aging look like for these materials, and does the ALD depositive layer change the degradation mode, or just delay the inevitable, basically?
Yeah, I think that's a great question. It's like the key of the entire work. We did not test too long of aging. These are all 2 hours at 800 Celsius. I did test 12-hour at 800 Celsius. That's like in a follow-up work that is not out yet, but I'll send it to you when it's out. But the short answer is that we believe we're just kinetically slowing down things. And a bit of that comes through in this graph, where you observe if the deactivation mechanism is truly, as we believe it is, this volatilization of platinum, what we're doing is we're significantly slowing it down. So we're not changing the chemistry of it. Like, this still happens. It is just so much slower that you can work with the same catalyst for a much longer time and not observe degradation to occur significantly, basically. Thanks for the question.
Super. And Lynn, a second question.
This is a question for Kristen. If you started out by motivating the recovering lithium from the complex of stuff that comes out of battery recycling, but there's all kinds of actually valuable and useful stuff mixed up in there. What's the strategy for that? Do you have to have one of these kinds of membranes for each thing you're trying to recover, or can you do some kind of cascade, or do it all at once? How do you attack that harder problem? Realizing, of course, that this is a completely unfair question, but nevertheless, what do you think?
No, this is an excellent question. So right now, with like industrial battery recycling facilities, it is typically like a step-by-step removal or recovery of one component at a time, just using like extraction or absorption technologies. So first you might try to remove the copper, and then you try to remove the nickel, and then the cobalt, and then lithium is typically removed at the end. One challenge they mention with battery recycling is if you remove the lithium first, it could potentially make downstream separation of all the remaining like transition metals a lot easier, because that's something that you could probably feed into like more of your standard like mining facility type refinery. So one thing that we're thinking of is if we could just remove the lithium first, that could potentially be beneficial for just simplifying the downstream process. And then, yeah, you just continue removing one thing at a time.
Okay, so lithium is one thing, but then there are all those rare earths. How quickly can you put China out of business on the rare earths separations?
That's another good question. So I would say like rare earth recovery is like another big topic for ion-selective membranes. Separating rare earth elements from each other is really, really challenging separation. But it is another like application that people are looking at for the development of these materials. We haven't looked at rare earth recovery yet in our lab. We're focusing more on lithium and some of the transition metals, but it is a big focus. I'd say there's still a lot of work that needs to be done to make very selective materials, though, for membrane separations.
Super. So this was absolutely fantastic. We're at time now. Thank you all for the wonderful questions. And let's thank our speakers this last time. One more time. Jabs, Jenny, Kristen, and Shraddha, thank you so much. This was super interesting and great results there. So thanks all.